Welcome to Unit 4, where we get to talk about the storage systems involved in servers. Now, as we looked at in the hardware unit already, desktop storage and server storage vary in a variety of different ways. Server storage can include more drives, higher RAID levels, and even allows for storage to be separate from the server that's using it. So let's talk through storage systems in more detail. Now, the first thing that we need to consider is the form factor and different mediums that server storage is going to come in. Much like with our desktop systems, we still have 3.5-inch and 2.5-inch hard drive form factors. Now, most servers are going to depend more heavily on the 2.5-inch form factor because we can get higher performance hard drives in this size. However, servers will use 3.5-inch drives when mass amounts of storage is the requirement. Now, there's a new form factor that's becoming extremely popular in both the desktop and server world, and that's the M.2 or the PCI Express SSD, which is significantly smaller than either of the other form factors, offers more bandwidth, and can connect directly to the north bridge of the system, offering superior performance over other storage mediums. Now, there's no one-size-fits-all for servers. We're going to use these different form factors in different scenarios based on what our server needs to do. As I've already mentioned, if we need mass amounts of storage, our 3.5-inch disk size is going to be preferable, primarily because we can get 18 or 20 terabytes on a single 3.5-inch drive. Now, we can only put about 12 of these in a 2U rack without getting a special storage style rack. But that gives us a significant amount of data storage and a significant amount of data density. 2.5-inch drives, however, are going to be limited to 1 to 2 terabytes for most spinning disks. Solid-state drives, however, can have 4 or 8 terabytes. There are even commercial products that have 64 terabytes on a single solid-state drive, but currently the cost of those drives is so far out of the ballpark for most people that we usually consider these to be 2 to 4 terabyte devices. So as a result, the storage density is still higher in our 3.5s, but our performance is significantly better in our 2.5s. Also, picture with me a standard 2U case where I have 8 to 12 of these drives, but I can have up to 25 of these particular drives, 2.5-inch drives, installed in a 2U chassis. While the overall storage of this system may be less because of the per drive capacity, the performance is going to be significantly faster, and that's going to make more sense when we get to RAID. If I'm striping across 25 of these drives, I'm going to get significantly better performance than if I'm striping across 12 of these drives. Also, SSDs only come in a 2.5-inch form factor today. So if I want the performance of a solid-state disk over a spinning mechanical drive, 2.5 inches is where it's going to be at. Of course, the ultimate performance, even better than striping across 25 drives, is still going to be my PCI Express M.2 connection. The problem with this is PCI Express lanes are limited. Even AMD EPYC with 128 lanes of PCI Express is limited in the number of devices that can be connected through that PCI Express medium, specifically these M.2 storage devices. Those lanes are also used for networking adapters, the South Bridge, and other devices within the computer. So while it provides more lanes for storage, we can still connect a significantly larger number of these 2.5 or 3.5-inch hard drives than we can our PCI Express M.2 cards. Notice also if we increase the size of our case, for example if we have a 4U or a 5U rack mount case, it's possible to get 96 or more of these 3.5-inch hard drives. If we get one designed for 2.5-inch hard drives, the data density, or at least the drive density, sorry, not the data density, but the drive density is increased significantly because we can get a lot more of these per rack unit than we can of these. In case you're unfamiliar with it, there are two different types of storage medium that are common today: spinning mechanical hard drives and solid-state drives. Our spinning mechanical hard drives have metallic platters inside of them that store data magnetically. These have been the standard for over 30 years and will continue to be a primary storage medium into the future. Newer to the game is the solid-state drive. Using flash memory, this drive has no moving parts, but uses flash memory to store information and has significantly higher read-write speeds than our spinning mechanical drives. Also, because it has no moving parts, they tend to last longer than our spinning mechanical counterparts. The problem is that when flash fails, it's significantly harder to recover a failed or dead flash drive as it is to recover a spinning mechanical disk. Usually the motor goes out on a hard drive, and so a data recovery service can remove the platters from this drive and put it in another drive that has a similar setup and can recover that data much easier than you can with a flash device that dies. There are also hybrid drives, a spinning mechanical hard drive that takes a small SSD and puts it inside the circuitry of the hard drive in order to essentially boost or cache the data on the hard drive to make it faster to access. Those have variable performance, and while they've been very popular in laptops recently, I would not recommend them for server systems. The performance of a spinning mechanical drive like this is determined by a series of factors. First of all, the spindle speed, which is measured in revolutions per minute, or RPM. The reason that this is an important feature of a hard drive is the faster that disk is spinning, the more data can be read and the lower the latency will be. Imagine a fragmented file that has pieces scattered around the disk. In order for the head to read that data off the disk, it's going to have to wait for that data to come around and then be read underneath the head, and then wait for the next piece of data to come around the disk and be read again. That fragmentation introduces latency in the drive. However, the faster that spindle is spinning, the less latency there will be because it takes less time for that data to make it around and get back underneath the head again. The downside of high spindle speed drives is that those platters then have a significant amount of angular momentum, which resists changes in direction. So if a server is shocked or bumped in some way, shape, or form, and the entire chassis moves, those metal discs inside will resist that movement, and the result can be damage to the motor or collisions with those hard drive reading heads. In any event, the faster the spindle speed is, the more sensitive these drives are to shock, and the more prone they are to failure. So while you get improved performance, there is also a higher risk of failure. Seek time is the metric concerning how long it takes for data to be discovered on the disk. When you ask for a file, how long does it take for the head to position itself correctly, for the platter to spin and get that data underneath that head, and the data to begin to be read? High performance drives will have lower seek times, thus improving the performance or the responsiveness of the system as a whole. The last specification, that's probably the most important, is the actual bus bandwidth or the transfer rate that the hard drive is capable of. Now this is a desktop SATA 3 hard drive, which means that the SATA 3 interface is capable of up to 600 megabytes per second read-write. However, desktop hard drives like this typically top out at about 110 to 120 megabytes per second of read-write. However, server hard drives, such as this Seagate Constellation, can provide data I/O up to 230 megabytes per second, significantly faster than desktop hard drives, but still significantly slower than the SATA 3 bus is capable of. When it comes to SSDs, as opposed to those spinning mechanical hard drives, some of those features or specifications go away. For example, we don't have a spindle speed on an SSD. And our average seek time is not a function of the rotational speed and the movement of the read-write head, but instead a function of the flash. And most often, the latency inside of an SSD is significantly small. Where the latency on a spinning mechanical drive may be 4 to 5 milliseconds, the latency on an SSD may be less than 1 millisecond. Similarly, SSDs are well positioned to take full advantage of the available bandwidth on a bus. Most of them are rated between 550 and 565 megabytes per second, which is pretty close to the maximum amount of data that SATA 3 can move. Newer SSDs will take advantage of things like SAS12 or SAS12 gigabit and SAS24 gigabit for even faster speeds. But of course, the fastest of all is still our M2 SSD. These M2 SSDs using PCI Express 3.0 or 4.0 in a by-4 configuration can reach speeds of 3 to 5 gigabytes per second. That's 30 to 50 gigabits per second of read-write. Now, unlike hard drives, our SSDs do have another metric that's incredibly important, and it's called IOPS, the input-output operations per second. In other words, how quickly and how many files can I access on these drives? While their overall throughput may be very quick, in other words, they can serve a large file at significantly high bandwidths, they may not be very good at doing small reads and small writes. It's important to note which drives have a better rating for IOPS, or input-output operations per second. Now these two happen to be good Samsung drives. This SATA drive is a Samsung 860 EVO, and this M.2 drive is a Samsung 970 EVO. Both of them are on the top tier of performance as far as desktop components are concerned, but there are even higher performing parts in the server world, both from Samsung and other companies like Seagate. Now, because we have such a variety of different storage mediums at our disposal, especially when we get into virtual machines or virtual hosts, we like to organize our storage in terms of tiers. Tier 1 storage is typically considered SSDs, or fast, high-performance storage. Considering that there's smaller space there, we have to be careful of the types of data that we store in Tier 1 storage. Operating system files and program files that are accessed frequently oftentimes will reside in our Tier 1 SSD storage. On the other hand, hard drives will oftentimes offer more storage space, but at lower speeds. We call this Tier 2 storage, and we typically store large amounts of data, backups, or files that don't need to be accessed as quickly or as frequently on our spinning mechanical drives. VMware divides up the storage tiers into 3 different tiers rather than just 2. They have extreme performance, performance, and capacity. Extreme performance would be M.2 drives or a RAID array of SSDs. Performance might be high speed or 2.5-inch low latency hard drives, where capacity would be slower hard drives with large amounts of storage. The interesting thing about creating these storage tiers with either Hyper-V or VMware ESXi is that those virtual hosts can actually dynamically allocate storage space on each of those different tiers. In other words, you can move highly accessed files to a different storage tier in order to improve performance, and as the usage of them lessens, you can move them back to another tier in order to free up space in your high-speed storage. As we've already mentioned, there's a couple of different interfaces that hard drives and SSDs will use in server environments. Now, typically in the desktop world, we just use a SATA interface, which we're very familiar with. However, of course, the M.2 PCI Express is becoming popular. In the server world, we also have SATA interfaces, but we have one level above SATA, which is SAS, or Serial Attached SCSI. A serial attached SCSI drive has a connector that looks very similar to a SATA drive, but it has some differences such that you cannot use a SAS hard drive in a SATA slot, but you can use a SATA hard drive in a SAS slot. SAS is specifically designed for high-performance server storage, has higher read writes, better cache on the drives are designed to offer higher throughput and better input-output operations per second. SAS will typically be our preference for server environments over SATA, however it comes at a higher cost. The older version of SAS, which was simply called SCSI, or Small Computer Systems Interface, was extremely popular in server systems but doesn't exist as much anymore. It was a parallel transfer technology that required special cables and terminators in order to make it work correctly. Of course, when it comes to external hard drives, USB is also going to be one of our most popular interfaces for external hard drives. Lastly, Fibre Channel. Now, I've mentioned before that the storage doesn't necessarily need to be in the same server that's using it. And we can actually have servers dedicated to storage or other locations where hard drives are being used to store server files. And we're typically going to use something called Fibre Channel to connect those devices together. While we're on the topic of storage locations, let's talk through a few different places where storage can be found. Now, we're most familiar with direct attached storage, which is hard drives that are physically inside the same case as the computer that's using them, typically connected via SAS or SATA connections to the motherboard that we would expect them to be connected to. Direct attached storage is what we see in the desktop world. However, in the server world, we have several other locations where data can be stored. The most remote is cloud storage, which we also see in the desktop world has become very popular with tools like Dropbox, Google Drive, or Microsoft OneDrive. But in the server world, we can actually leverage cloud storage in different ways than we would with a desktop. We can even boot computers off of cloud storage if we set it up correctly. Between direct attached storage and cloud storage, there's a couple of different levels of network attached storage. The first one is simply called network attached storage. This uses either the Linux network file system or the Windows SMB server message block to essentially create a layer 4 communication between a server and a hardware device. If you've ever done a file share across the network, that's essentially what a network attached storage medium looks like. It's a hard drive in another device that you can access through a shared folder. The advantage of this is it's fairly easy to set up and also very secure. The disadvantage is there is a lot of additional overhead in communicating between a network attached storage device and a server, which makes it less efficient than some of our other network attached storage methods. iSCSI or Internet SCSI is going to be one level above our network attached storage. iSCSI essentially allows us to drop down to layer 3 or IP address layer communications in order to get rid of some of the overhead that we have at layer 4 with that TCP connection for network attached storage. iSCSI can be implemented from the BIOS level to connect a server out to a remote server that is offering storage via iSCSI, and we can even boot servers off of iSCSI targets out on the network. While faster than network attached storage, iSCSI is still not the fastest network-based technology that we have. Fibre Channel over Ethernet is one step above iSCSI. Now, despite its name, it doesn't actually have to use fiber optic cables to connect the server to that network. But oftentimes we do use fiber in order to get the improved throughput and faster data access that we're looking for at this level. Now, much like iSCSI moved us from layer 4 to layer 3, Fibre Channel over Ethernet moves us to a layer 2 protocol as opposed to a layer 3, thus continuing to reduce the overhead necessary and increase the actual data throughput. A caveat of this particular technology is that we actually have to start looking into specialized networking devices, specifically Fibre Channel over Ethernet switches, which are designed to work with Fibre Channel systems and connect computers together so that they can access storage that's hosted on a variety of different devices very quickly. Now, in order to get the most out of Fibre Channel over Ethernet, we'll go one step further to our fastest remote storage technology, which is called a Storage Area Network, or a SAN. Now, this takes the idea of Fibre Channel over Ethernet and then isolates all of that network traffic in its own network specifically for moving data between servers. This eliminates any congestion from other network traffic, such as internet traffic or Active Directory, directory services traffic that might be on the network, and protects the resources of that network so that it has the maximum amount of available bandwidth solely for moving data from where it's stored to where it's being used. Storage area networks have extremely high performance but come at a premium cost. But they are an excellent way of dividing the computational power of servers and the mass storage required for those servers by collecting the hard drives required into additional units or into large RAID arrays that are physically separate from the processing nodes that are actually going to be using that data. So really quickly to review, direct attached storage is going to be inside the same case as the computer. Network attached storage is going to use layer 4 communication, much like network attached storage does in the desktop world. iSCSI is going to be one step faster than network attached storage, using a layer 3 protocol to move data between remote devices and that server. Fibre Channel over Ethernet is going to elevate us one step further by moving down to layer 2 communications. And then if we isolate a Fibre Channel over Ethernet system into its own isolated network, get rid of any other traffic, that's called a storage area network. And lastly is our cloud storage, which is going to have the lowest performance, but a lot of features such as redundancy and multi-location backups become available if we use cloud storage. Now, a couple comments on storage capacity, or the capacity of individual hard drives. When manufacturers advertise hard drives, they tend to calculate disk space based on base 10 calculations, which means that a gigabyte is actually less than a real gigabyte, since computers use base 2. In other words, 1,000 kilobytes would be a megabyte on this particular hard drive according to the manufacturer, but the computer is looking for 1024 or 1024 kilobytes to be a megabyte on a hard drive. Because of that, when you plug in things like 500 gig hard drives, you'll typically see the storage reported as 465 gigabytes. And that's simply a reality that we have to live with. Marketing doesn't always match the technology. Of course, for the most part, hard drives are inexpensive enough that it's easy to get something that's larger than we need, and we're not usually counting gigabytes to make sure that we can fit our data within that drive. Now, of course, once we have a hard drive, there are many things that are going to take up space on that drive before we actually get the data that we need onto the drive. The first thing is the file allocation table. Now, whether we format this with NTFS or FAT32 or exFAT or ext4, ext3 over in the Linux world, whatever it is, there's going to be a table that stores all of the information of where the files and directories are on this drive. And the larger our drive is, the larger that file allocation table will become. In fact, on large drives like this 2 terabyte drive, that file allocation table may be tens of gigabytes in size. So right off the bat, we're going to start to lose capacity on our drives just because we need a table to keep track of what is on our drive. After that, data is quickly going to fill up our drive. If we install an operating system on this drive, that operating system is going to take up space. Windows typically takes 20 to 40 gigabytes of space. Then drivers will be added in order to access the hardware or use the advanced features of hardware. Additional programs, applications, other software, the services that our server needs to offer are also going to start eating into that space. Log files, backups are going to continue to add usage to that drive as time goes on. And before you know it, your drive is going to be full. So planning ahead and knowing what you're going to be doing with that drive and maybe even overbuying from the onset is a good idea. There are a couple different tools that we can use to protect the storage space on a drive. For example, we can set up disk quotas, which allows programs or users to only use so much data on a drive before they're cut off. This can be advantageous if we have a shared folder that many users in a company are using to prevent any one of them from using up all of the resources on that device. The downside is, however, if we also limit the amount of space that a program uses, if that program gets to the point where it's about to exceed that quota, it may cease functioning correctly because it doesn't have the storage that it needs to perform the task that we've asked it to do. In the virtual machine environment, we can solve some of this by using thin provisioning. But remember, thin provisioning, while it allows us to oversubscribe disks, if they end up using all of the space that we've allocated to them and we've oversubscribed that disk, we're going to fill up that drive, and as soon as the drive is full, those operating systems are going to freeze because they don't have a place to write the files that they need to write. Monitoring disk usage in that particular case is very important. Another thing that we can do is compress the file system. Now, this became very popular in the days of Windows XP and floppy disks, if you can imagine. Floppy disks used to hold 1.44 megabytes of data. Wow, almost a half a song or 1/4 of a picture today. But in order to increase the capacity from 1.44 megabytes to 1.68 megabytes, you could actually compress a floppy. And it would essentially apply a compression algorithm to all of the data on that disk, similar to zipping a file in the desktop world or using tar to compress files together. Windows XP actually had a feature where you could compress an entire NTFS drive, and the operating system would go from using 4 gigabytes to 3 gigabytes of space on your drive, thus freeing up more space. The problem with this is every disk operation then has to go through both memory and CPU to be decompressed before it's accessible as data that's readable. And as you can imagine, that introduces a significant amount of latency and severely hinders the performance of a computer. This should not be used except for at the uttermost end of need. As Lord Denethor would say. Please cut that from the video. The last thing that we can do to protect storage is something called data deduplication. Essentially looking through a drive and making sure that we don't have multiple copies of the same file. Oftentimes when programs install, they install shared files that they need in order to run. And sometimes multiple programs who need the same program will install multiple copies of that same program. Deduplication can remove those duplicate files and reduce the amount of storage that's used by programs and the operating system. Let's talk about making disks usable. Now, much like the hardware in a server requires an operating system or software, in order for us to actually leverage the CPUs and memory and graphics that's inside of a computer or inside of a server, Hard drives also need another layer of essentially software in order to make them useful, and we call that the partition table or the file system. When we initialize a disk, we have two options for initializing, MBR and GPT. MBR, or Master Boot Record, is the older style of initializing a disk, and it essentially records in the very first sector of the drive the layout of that disk, the partitions that exist, where each of those partitions start, and whether or not any of those partitions are marked as active or bootable. MBR has served the computer world for multiple decades. However, it's slowly falling out of favor, in part because it has a maximum drive size of 2 terabytes. And many of our hard drives today are 4 terabytes and larger. And so GPT, or the Global Unique Identifier Partition Table, is growing in popularity. GPT has the potential to be used on drives up to 9.44 zettabytes, which is a significant amount of storage space that currently is unfathomable. But realize that even 20 years ago, the idea of a 1 terabyte drive seemed completely impossible. GPT has several features to it, including the fact that it's more resilient to failure. MBR drives can sometimes lose their file allocation tables or their formatting, where GPT drives are a little bit less likely to do that. The downside of GPT is that it requires both 64-bit hardware and a 64-bit operating system in order to be used. And that's due to the fact that GPT uses 64-bit addressing, which is one of the ways that it is an improvement over MBR and has the ability to address such a large amount of disk space. There are also limitations in the number of partitions that you can have with an MBR drive. However, in a GPT drive, you can have almost an unlimited number of partitions. Once you partition your drive out, most commonly today we tend to have a single partition on a drive, we need to give that partition a file system. Now there are tons of file systems available today, but let's just talk about the most popular ones real quick. In Windows, FAT32, exFAT, NTFS, and ReFS are the 4 most popular formats. FAT32 has a long history inside of Windows, has a very efficient file allocation table, but limits the maximum file size to 4 gigabytes and doesn't store permissions with the files. NTFS has essentially replaced FAT32 for all intents and purposes as the primary Windows file system. NTFS has a larger file table, allows individual files to be significantly larger than FAT32, and does a great job of storing access control lists with the files, which is required for Windows to be installed. In other words, if you want to install Windows, it has to be on an NTFS partition. exFAT, which is essentially FAT64, has also become significantly popular in the Windows world, particularly in thumb drives and external drives. It doesn't have the same limitations for file size and drive size as FAT32 does, but it also doesn't have the access control list features that NTFS does. So it's a lighter weight file allocation table, very useful for external drives, but is not a viable target for installing Windows. ReFS is a file system that was introduced a few years ago, and it's come and gone in popularity and seems to be on the way out at the moment. But it was essentially a contender for replacing NTFS as a more reliable file system for server systems and workstations. On the Linux side, we also have a myriad of different file systems that are available. But the most popular are ext 2, 3, and 4, which are journaled file systems. UFS and ZFS are also popular in Linux. Now when we get to virtual machines, realize that we will create virtual hard drives that use some of these different partition styles. But the drives themselves will actually have a different format that NTFS, FAT, or ext3 or ext4 file system sits on top of. VHD or VMFS formats will be used, virtual machine file system or virtual hard drive.